Go. All right, so we talked about a little bit about ER design. Oh yeah, when you come to draw your ER diagrams, and here I'm talking about assignment 1 again, if you've got any decent, reasonable, realistic data model, it's not going to fit on it. It certainly won't fit on a single VGA size screen. So often what we do is we'll define the entities separately. So we'll have an entity and all of its attributes. We'll have another entity, all of its attributes, another entity and all of its attributes. And then at the end we'll have a diagram that just shows the entity boxes and relationships between them. So that's a reasonable way of trying to fit everything, or trying to handle a large amount of information. And you might even need several diagrams showing relationships if you've got a very large one. Alright, speaking of large scenarios, here's a possibly largish one. Alright, this is going to be difficult. I can't fit everything on the screen at once. Alright, so what kind of entities do we think we've got in this system? And remember, I said entity, I'm sure one of the slides said noun entity or noun attribute, and verb tends to be relationship. Aha, there's a noun. Okay, so we'll probably have patients. There's another noun, we'll probably have doctors. And here we had that diagram a couple of slides ago that had classes and subclasses. So what we'd be looking for, if we're talking classes and subclasses, we need a superclass. And what we're interested in is what are the common attributes between patients and doctors. So patients and doctors both have social security numbers because they come from the US. They both have names. Doesn't mention the address for a doctor, so at least there's two common fields. So social security number and name. So we could have a superclass called person or whatever, and then subclasses patients and doctors. The differences is in the case of patients, we're interested in address and age. And for a doctor, we're interested in what they're specialised in and how many years of experience they've got. Oh, and here's another type of person. So once again, a pharmacist has social security number and name, and this time we're talking about qualification. So a pharmacist is different to a doctor. So I reckon we could, let's see, I had it set up so I could actually draw a diagram. Ha ha ha. Alright, let's see. So we got a person. Every person has a social security number, which importantly is unique, therefore giving us the key, and a name, I believe. And we need to try and do this as quick as I can. This is a nice drawing tool that the Mac has. And I'm sure, I mean, you guys have probably got access to other drawing tools, and especially ones that are specialised for drawing ER diagrams. Alright, so that looks good. Somehow I've got can't do it. I've chopped away a whole lot of the components. Let's see, can I adjust it? I need to put an underline. Ha! I know what to do. get one of them. Voila. Alright, so the person's has a social security number which is unique and they have a name. Right, and then we had and then what we need is, we don't need an attribute, what we need is a circle. And we think about whether they should be disjoint or overlapping. Oh, I should say what the subclasses are first. So we've got patients, we've got doctors, if I can spell, doctor, and we've got pharmacists. What do you reckon? Actually, this one's a little bit interesting. So, any person, I would argue, can be a patient. A doctor could be a patient, a pharmacist could be a patient. I'm going to push this up a bit. But, can someone be both a doctor and a pharmacist? I would argue unlikely, because they both require a lot of training, and to spend the amount of time to become a doctor and then become a pharmacist would probably be prohibitive. So we want to be able to say that doctors and pharmacists are disjoint. So you can't be both. But any of them could be a patient. So that's actually going to require another level of subclassing. So at this level, we've got overlapping subclasses, and I should try and make it into a circle. There you go, looks a bit like a circle. So a person, what's going on there? Alright, so a person could be a patient, or they could be one of these other two. The only way we can actually represent that is to add another level and have a different subclass and put these guys under, or girls, under that subclass. Oh, but we can't do it directly like that. So we can have patients, and we can have, I don't know, medical professionals. That too. Medical professionals. Okay? So two different subclasses of person, and under medical professionals we've now got disjoint subclass. So you're either a doctor or you're a pharmacist, but you can't be both. However, anyone who's a person, which is basically anyone, could be a patient or they could be a medical professional. Alright, so let's start sticking in some lines to make it all fit. Oops. You should try doing this without a mouse. Pretty difficult. Now, at this point, we could argue that that we wanted everyone in this system to be one or the other. Probably fair enough. So, Oh, it's bad. I got rid of too much of the editing stuff. Can I get it back with that? With that? Nope. Show sidebar. Wrong sidebar. Anyway, you've got to imagine this is a bold line. Ah, I know what to do. I can put a second line. No big deal. What? See, I didn't want the end or there just to make it look different. Right, so that's meant to be a thick line. So every person is either a patient or a medical professional. And we're simply going to have to do the same kind of mess down here. Because every medical professional, I guess we can argue that, yeah?
Is there a reason that as I mentioned?
Oh. Yeah, I should have read the rest of that thing, that's right. Where is it? Here. So, you're asking about pharmacists managing a pharmacy? Is that right? Each pharmacy, a pharmacy must have a manager. Oh yes, good point. I was kind of assuming that the pharmacist at a pharmacy would be the manager. You're potentially right. We could have a separate manager type who would not be a medical professional and would not be a patient. Yeah, all right. Let's add them. That sounds fair enough to me. Come back here. Right, this is what happens when you do it on the fly. Didn't want that. Go away. Alright, so that's another type of person. What is that thing? How did that end up like that? Oh, it's so tedious to watch, isn't it? I'm trying to avoid touching that line. Gotcha. Alright, so we can go there. Yeah, so a manager can be is another type of person, neither a medical professional, can be a patient though. Oh no, oh no, a manager can't be a medical professional. Well, maybe they could be. Interesting one. What to do then? Oh, we're going to end up with 3 levels of subclassing. So we've got patients and non-patients, and then under them we'd have managers and medical professionals, and then under medical professionals we'd have what we've got here. Alright, let's assume that a manager could be a medical professional. So maybe a pharmacist could be a manager. Once again, I think I decided that this needed to be, oh, it kind of looks thick just by doing it. Anyway, that. Okay, so a person must be either a patient or a manager or a medical professional, and could be more than one of those things. And a medical professional must be either a doctor or a pharmacist, but can only be one or the other. So it could be a doctor, it could be a pharmacist. All right. So what's interesting about a patient that is more than just being a person And if we go back and look at the requirements, I think we're going to find one of the things was age. But remember, we decided last time that age was not a great thing as an attribute, so we'll use date of birth. And the other attribute, if I remember correctly, for a patient, address. We need their address. Okay, so I think that's everything we needed to know about a patient. So for a given patient, because they're a person, we have a social security number and a name, but we also have an address and a date of birth. For a manager, see, this is now where it starts to get slightly messy. What information does a manager have that's not specific to anyone else? A pharmacy must have a manager, so it doesn't say anything about the manager. Okay, that's fine. So we don't need to add any extra attributes for the manager. In fact, it turns out that the manager is only involved because they have a relationship with a pharmacy. Okay, so that's the real issue for having those kind of people. So we know they're a person, we know they have a social security number, but they don't have any additional attributes. The whole point of putting them here is that they are involved in a relationship with a pharmacy, which sounds a little bit weird, but we're talking ER here. Alright, so but doctors and pharmacists do have additional information, and if I can click on the right thing. So a doctor has got, we've already handled name and SSN, specialty, years of experience. And once again, years of experience, changes every year, so that's probably not a good idea. Maybe we can put the year that they started, and then we could always compute the years of experience from that, assuming they didn't have an extended break in jail or something. So a doctor, so two more attributes. Oh yeah, they fit there all right. Let's assume that people start practicing as soon as they graduate. So maybe, right, so we can do it that way. So a doctor has a particular specialty, like, you know, oncologist or pediatrician or whatever, and they graduate in a particular year, and from that we can infer how many years of experience they have by making certain assumptions. And it's interesting, we don't seem to care about the doctor's degree, which I always thought was a bit strange, but that was the way the problem was phrased. But we do care about a pharmacist's qualifications. So that was one of the other pieces of information associated with a pharmacist. Where is it? Where? A pharmacist can only work for one pharmacy. Clearly, that's going to be involved with a relationship. There's a relationship involved there, and we get some clue, can only work for one pharmacy. So we may have a pharmacist who's not working for any pharmacies, but they can work for at most one pharmacy. For each pharmacist's name, alright, we've already handled that, and qualification, so there's only one extra attribute to be put in here. too long if I type the word in full. So that kind of captures, I think, all of the information about people. And so we've got this quite intricate class hierarchy involved. All right, so let's take a look at what else we've got. What other kind of entities do we have here? There's another noun. So we've got drugs, and they have information associated with them, trade name and formula. So that's looking like an entity with two attributes. Every patient has a primary physician. Okay, so this is clearly a relationship between a patient and a doctor. And when it says has a, you can imply one primary physician. Therefore, we're going to have an association between patients and doctors. Every doctor has at least one patient. Okay, once again, that's telling you about the participation constraints on that relationship. Each pharmacy sells several drugs. Oh, what happened to pharmacy? Oh, pharmacy has a name, address, and a phone number. Each pharmacy must have a manager. Right, so clearly there's another entity, pharmacy, with name, address, and phone number. Not going to bother drawing that because it's taken too long. Drugs, another entity with a trade name and a formula. A pharmacy sells several drugs. It would be unusual pharmacy that only sold one. So here we're talking about an end-to-end relationship between pharmacies and drugs. A drug might be sold in many pharmacies, and a pharmacy sells many drugs which are actually told there. A drug can be sold at several pharmacies, and like that example we had a couple of slides ago, the price of the drug could vary at different pharmacies. And then we've got prescriptions. Okay, so doctors prescribe drugs for patients. Doctor can prescribe multiple drugs for several patients, and a patient can obtain prescriptions from several doctors. So that's telling us all about the relationship between doctors, drugs, and patients. So that to me is looking a little bit, could be done as a three-way relationship. I got some, fleshed out examples that I could show you, but let's start trying to do some of those relationships that I just talked about. This stuff. Oh, I should have put a thick line as part of my palette, shouldn't I? Alright, so we'll leave that stuff up there and go down here and start. Oops, forgot to. Relationships between doctor and patient. I'm just wondering, oh, I could have done this earlier. What a goof. Let me see. Damn. Thank you. There's probably arrows somewhere as well, which I might need any minute. No, that's flipping the... No. Right, might have to pretend there are arrows. Oh, what's that? It's an arrow-looking type thing. Nope. Not going to help me. Style. Nope. Oh well, doesn't matter. Okay, so let's go and have a look at relationship between doctors and patients. So every patient has a primary physician. Every doctor has at least one patient. So these we've got to capture. Now there's actually two relationships there. There's the relationship is primary physician, and there's the relationship that a doctor sees a particular patient. So, We'll need to capture both of those relationships. So, is primary and C's. That's interesting. All right, so what about the cardinality? Every patient has a primary physician. So we're going to need one of these. No, we're not going to need one of them. We're going to need one of these. So every patient is associated. Hey, why did that change? Is primary. And this is where it's going to fall in a hole because I can't get my arrow. But there should be an arrow there because every patient has one primary physician. Okay? So every patient has a single primary doctor, physician. How can I simulate an arrow? I don't know. Anyway, I'll add the arrows onto this diagram later. Alright, doctor sees a patient. If you're a patient because you're seeing a doctor. So I would argue, wow, that's pretty weird. I would argue that this also has to be total participation. So something like that. Now, these sides I've left non-total. That one's a little bit debatable. A doctor might see no patients. That's what that says. A doctor can see 0 or more patients. A patient is seen by one or more doctors, okay? One or more because of that total participation. A doctor, and more plausible, a doctor may not be the primary physician for any particular patient, so it makes sense to leave that partial. But there should be an arrow on the end of that line because every patient is associated with one primary doctor. Now the C's relationship, we're not actually told anything extra here. Doctors prescribe drugs, so we haven't done drugs, so to speak. Don't do drugs. Every doctor sees at least one patient for each drug, trade name and formula, so we've got an entity drug which has 2 attributes. We could have a look at the relationship between pharmacies. Oh, and we've got another entity, pharmacy, which I'm not going to fill out, name, address and phone number. Alright, so let's go back here, scroll across a bit and talk about the relationship between what do I do? I just deleted everything I drew. No, I didn't. That would be unfortunate. Alright. So here's our drug drug entity and pharmacy. Alright, so a drug may or may not be sold at any pharmacy. That would be slightly unusual, but I guess we can leave it as partial participation. And every pharmacy is not much of a pharmacy but doesn't sell any drugs, so it would make sense to make that total. And this is clearly going to be an end-to-end relationship. A drug may be sold at many pharmacies, and a pharmacy may sell many drugs. The other thing, like that diagram that we had before, there's going to be an attribute associated with that, the price of a drug at a particular pharmacy is an attribute that's going to be associated with the relationship. That's basically analogous to the thing I had before. And on drugs, we've got a trade name and a formula, so there'd be two attributes there. Pharmacy, we've got a name, address, and so on. So that's getting part of the way through that rather large, complicated thing. As I said, I've got a complete version of that. It might even be one of the examples in the exercises, so you can go and have a look at the final solution. Boy, I'm choosing some unfortunate phrases today, aren't I? Right, so there's another example, book publishing, also in the exercises. It's going to take too long to go through that here, so let's press on. So, entity relationship model, very useful for doing data modeling, building a design that is reasonably easy to understand. You can structure it hierarchically. Here's all my entities, here's the relationships between all the entities. Can capture a lot of details, but as we'll see, it doesn't capture all the details. Like for a student ID, if we talk about UNSW, there's nothing in the ER diagram that says the student ID has to be 7 digits long. We definitely want to capture that information somewhere, and that's going to crop up when we start writing SQL schema for those kind of problems. We've got entities, relationships, we've got relationship constraints, and we've got classes and subclasses, and we've got weak entities. One slightly annoying thing is that pretty almost every textbook uses a variant of ER notation. Some of them actually put the cardinality on the lines between entities and relationships, so you don't have to infer stuff from arrows and thick or thin lines. But yeah, like I said, if you pick an arbitrary textbook, you're going to find something different. I think the notation that I've been using here is kind of a blend of the Stanford book and the Korth Silverschatz book. Alright, so now we've got 10 minutes to look at the relational model. Alright, so the ER model views the world as entities and their attributes and relationships between entities, and maybe attributes on the relationships. The relational model is simpler than that. We view the world as a collection of relations. That's our only structuring formalism that we've got in this model. You might say, that sounds a bit limiting. How do I capture relationships? How do I capture subclasses? How do I capture multi-valued attributes, and so on and so on? We'll see. Relations can do everything, I think. Right, so the relational model, very simple, very general. And it's a formal model, and you can reason about descriptions in the relational model, you can do proofs, We'll see some examples of things like that later on when we talk about functional dependency and so on. So it has a nice formal model, but it's also easy to implement. So if you talk about a relation is just a collection of values. So it's like a struct in C. So really, you can be talking about, hey, here's a struct, here's another struct, here's another struct. I write a bunch of structs in a file, and that gives me a relation or a table. When people talk about it, because there's these two notions, there's this formal notion and there's this data structure notion, there tends to be two different types of terminology. So we can talk about relations, or we can talk about tables, talk about tuples and records, talk about attributes and fields. Okay. So this basically treat them as synonyms. All right, so a relation formally corresponds to a mathematical relation. So you've got a mathematical relation is a set of tuples basically that say this thing is related to this thing is related to this thing is related to this thing, and it's all the same kind of relationship. And if you've got a set of tuples like that, there's a relation. But you can also view it as a table or a file if you want. So a relation has a name and a set of attributes. In the pure relational model, we don't talk too much about the types of the attributes, but technically every attribute has a name. It could be student, ID, course, program, course title, whatever. And there's also, each of those attributes is associated with a particular data type, which in database terminology is called a domain. So it defines the set of allowed values. So for student ID, this W, 7-digit number, starting with either 2, 3, 5, or 9 at the moment. Eventually it'll start with 6 and things like that as well. Actually, it's going to be interesting when they run out of 5s and have to go to 6s, because then you've got the people that started here in the 60s who will also have IDs that start with a 6. Anyway, I'm sure they'll be able to resolve that. So a domain. So something like a name, it's just a string, an address, just a string. Maybe the string has some internal structure, like you might use comma-separated things. You might write the street name, comma, city name, comma, postcode, comma, country, things like that. But as far as the relational model is concerned, it's a string. We don't deal with the internal structure, and as far as the relational model is concerned, every attribute has a single atomic value. Right, so that's the critical thing. And also we can talk about constraints, which we just write as expressions like student ID greater than 0. That's a pretty stupid example. Mark greater than 0 and mark less than or equal to 100. Things like that. Right, so here's a typical way, and I love this example, which I got from one of the textbooks. I think it was the course Silvershat's book. So it's a bank example, so we're talking about accounts. An account is held at a particular branch. Apparently in this system, the branch name is good enough to uniquely identify the branch. Account number, clearly they've been designed to uniquely identify the account. And of course the balance. So if we want to talk about domains, that's, domain is real numbers, probably, positive real numbers, although I've written everything as an integer. Account number, it's a string, but it's a string with a particular structure. So the structure would be specified in terms of constraints. The domain is simply string, and the branch name similarly. So the collection of these things, each of these rows, we can call it tuple. That's generally what I'll call them. And I'll generally call fields for the components of a tuple. So along that row there, that's a single tuple, that's another tuple, that's another tuple, and so on. and a collection of tuples which all have the same set of attributes, all with the same domains, form technically a relation, but we normally call it a table. So very simple structure. Everything is represented by one of these things, including relationships, and we'll see how to do that next week. Attribute values must be atomic, so there are no composite and no multi-valued attributes. Interesting. The ER model allows us to specify that we do have multi-valued attributes. How are we going to represent that in the relational model? And you'll see next time. In the relational model, there's a value null which can be used in any column or any field. And basically, there's been a few database nerds who've complained about the imprecise meaning of null. Sometimes it means don't know. So here's a field, I've got to put a value in, I don't know what value to put, so I'll just stick null there until I work it out. It could mean not relevant. So the example I give is if you've got male and female, and one of the fields is how many children given birth to, or something like that. So in a male tuple, it doesn't make sense to talk about that field. In a female tuple, yes, there could be a numeric value, which could start at 0. And there are a couple of other meanings for null. So, as I said, because it's not precise exactly what null means, some people don't like that. And a relation has a key. This is true in the relational model, the pure relational model, which is what I'm talking about here. Once we go to SQL, a table doesn't have to have a key. What else? All right, so relation schema basically gives the name of the relation, the name of the attribute, and the domain of that attribute. And a tuple is basically just a collection of values from these domains, and an instance of a table is just a set of tuples of that type. A database schema is a collection of relation schemas. Sometimes this gets a little bit confusing, but a database is just a collection of relations. And if you want to be technically correct about it, talk about a database instance. So I could have, the notion of a university database which has students and courses and enrolment and stuff. There's a version, an instance of that database might be used at UNSW, a different instance would be used at Sydney Uni, a different instance again would be used at University of Wollongong. The database itself has exactly the same schema. We've got the same tables with the same relation schemas, if you like, but we have different sets of tuples in each of those tables in the different instances of the database. All right, that will do. So see you next week.